Oh, yeah. Yeah. All right. So, as she said, I'm Isabel Villaneda-van Vloten, and this summer I analyzed the compaction of the Niobrara Formation in the Julesburg Basin. And so this is a part of a larger project studying the pore systems and connectivity in the Niobrara Formation. That's Dr. Budd's project. All right, so the reason we're interested in the Niobrara is because it's a currently active, unconventional resource play. So what makes it unconventional is that we have very low permeabilities, but with the economic everything that's going on, it's making it feasible for us to try to get these hydrocarbons out. And then the Niobrara itself is a series of alternating chalks and calcareous shales, which were deposited in the western interior seaway. So it was an epiperic sea, and we had all sorts of little critters making stuff, and that's what the Niobrara is. And so you'll see Colorado's in that little circle, which is my field site. And it was deposited in the late Cretaceous. All right, so my research question this summer was, how does the degree of compaction correlate to lithologic attributes? So because permeability and porosity are the limiting factor in finding hydrocarbons in this formation, it's very important to us. And generally, with compaction, you ruin porosity and permeability, as you see in this diagram. So we wanted to know at what scale can we categorize the compaction. And we wanted to know whether we could categorize it at the stratigraphic zone, at facies, or at individual grain size. All right, so more about where we're at. As you see right here, the pink is the Julesburg Basin. And you'll notice that the Niobrara outcrops out here. And so it'll deepen down until the frontier. And let me find the pointer. I got this. Okay. So this area has been drilled for decades. And because it's a lot shallower, there's a lot less issues with permeability. But we're interested in this area now, which is why my work is important. And this once more is just becoming more specific on what area we're in. We're in Wells County, and we had available core from 4 wells, and the 2 wells that I was able to get to thus far are the Timbro and the Aristocrat. And this is the Wattenberg field for reference. All right, so the Niobrara split up into the A-chalk, A-marl, B-chalk, B-marl, C-chalk, B-marl, D-chalk. And the area that I was looking into that we had samples for was the bottom of the A-marl to the top of the C-marl. And I have thin section samples at about every 2 feet through that section. And the B-chalk is the traditional landing zone for unconventional oil, so that's the area that they focus on when they're drilling horizontally. All right, so in order to study compaction, I was looking at pelloids this summer. So pelloids are alchems composed of micrite. What that means is they're grains of recrystallized calcite. And then within that, there's 2 categories. Pellets, which are fecal pellets. I think you can assume what those are. And interclasts, which are mud lumps, and they're shell fragments. And the nice thing about pelloids is that when they're deposited, we can assume that they're deposited round. So by studying the forms they're in now, we can see how much compaction has occurred since they were deposited. And that's a little sample picture up there. Kind of looks like chickenpox or something, but they're pelloids. All right, so in order to measure compaction, we had available core from all of these wells. We had thin sections made at about every 2 feet. I took photographs of them in the microscope, and then I imported them into ImageJ. And what ImageJ allowed me to do was go in and manually pick out all of these pelloids. This is a little bit difficult to see, but this is what a lot of my summer was spent doing, was just outlining these little pelloids. And then by outlining them and using ImageJ, I was able to take these measurements. And out of these measurements, we did some preliminary graphs and stuff, and we found that the best proxies for our study were perimeter, circularity, and mean grayscale value. So perimeter, I'm going to assume we all know what that is. Circularity is basically how round it is in comparison to a circle. So as you'll see, that pelloid has a lower circularity. It's more compacted. And then this pelloid is more round and it has a higher circularity. And then with a perfectly circular pelloid would be at 1. All right. And then we have mean grayscale value. And this one's a little bit counterintuitive because we have darker colloids are going to be smaller numbers, and lighter colloids with higher numbers. So once we had all of our colloids picked, which were 50 per slide, and I had about 30 pictures per well, there's a lot of colloids. We went ahead and looked at some basic stuff to figure out what kind of colloids we had. So first, we made a histogram of overall circularity by well. You'll see the Timbro is in green, and the Aristocrat is in red. And what we found is that we had a wide range of circularity. We're ranging from less than 0.3 to more than 0.9. And what was also really nice is that we had about the same circularity within the two wells. So wide range of circularity, consistent across wells. Next, we looked at the overall pelloid size. So again, it's all of the pelloids we studied. And what we found is that there's one primary population here, and you have a minor positive skew here from a minor population. And once again, we were consistent across both wells, which is really nice. One primary population, minor influence for a second. All right, so then we started trying to compare it down to scale. The first scale I used was stratigraphic zone by its predominant lithology. So I mentioned I had the B chalk and the C chalk and the A marl, and so I lumped those together. The B chalk with the C chalk, the A marl with the B marl, and the C marl. And what we found is that there seems to be a little bit of a trend, but it wasn't significant. So we're saying this is probably not a scale we can categorize compaction at. So next, I went to stratigraphic zone individually. I plotted circularity by depth, and you'll notice that the Niobrara lies at different depths in these two wells. And then I set them up by the stratigraphy. And what we found is that there's a lot of variation within each stratigraphic zone. You'll see for this one, it's going from about 0.65 to all the way to 0.8. So we don't think that this is a good scale to categorize compaction. Next, I set up some microfacies. I categorized everything into 7 categories. I categorized all my slides into 7 categories, primarily based on foraminifera abundance, the balance of chalk to marl, and the different structures, so whether it's fire-turated or laminated. And what we found is that there seems to be a little bit of a trend. We see that microfacies 1, 2, and 4 tend to come together at a lower circularity, and facies 6, 5, 6, and 7 tend to clump together at a higher circularity, with 3 being an intermediate. But by looking back at the data and trying to figure out what these microfacies had in common, didn't find anything. So I think that this one wasn't very conclusive. But when it got exciting was when we got to the grain scale. So as I said before, our color proxy was mean grayscale value, and it's counterintuitive, so I'll remind you because I reminded myself plenty of times. We have the lower values are darker, and the higher values are lighter. And what we saw was a really strong trend. We had statistically significant correlation to greater than 99.9% confidence level that darker pelloids are going to be more compacted and lighter pelloids are going to be more round. Right, so in conclusion, we see that there's one primary organism with a minor influence from a second larger organism. We see that compaction is not well categorized by the lithology of its corresponding stratigraphic zones. We see that degree of compaction does not correlate to stratigraphic zone well. And we see compaction is better categorized by microfacies, but perhaps recategorizing those would be more conclusive on that scale. And we see that darker pelloids show higher compaction than lighter colored pelloids, which is our exciting result. And recommendations for the future, which I wasn't planning on continuing this study, but it was so exciting, so now I'm just going to continue it. So we want to increase the number of wells sampled. As I mentioned, we have 4 wells available, so I hope to finish out those last 2 wells. And we want to, I ideally would like to sample more marls. I didn't choose which sections we sampled within the course And we have a bias towards picking chalk even within the marl subfacies. So I think it would be great if we could sample more marls. And also helpful would be chemical analysis, so we have a better idea for how much chalks there are and what pelloids composition is and stuff like that. And also, I would like to find a better proxy for color. I'm using the mean grayscale value, but it really isn't taking into account the hue and other factors to color. And I would also like to find a less temperamental program for analysis, because the program I'm using, ImageJ, wasn't intended to be doing these type of things. It was kind of annoying. And I want to thank these people, because otherwise none of this would have happened. Thank you.
Question? What happens if you pitch the, now I forget which one's dark and which one's light, the leftmost 3 samples, the 3 darkest ones?
So what do you mean pitch them?
So
they're
just
those 3 points?
Yeah, they're sort of, and then maybe the one off on the right, because they're just sort of, no, but no, seriously, they're just like,
yeah.
They're off in their own neighborhoods.
Then you would ruin my day. No. No, that's the thing is, that's part of why I want to get a larger pool of samples. And then these are the average values for each sample. So the more samples we can get, we can definitely make, because it's very significant, and that's kind of weird.
Yeah.
But I want to know too. Sorry.
Yeah, that was a very nice presentation. My question is about the pelloids and their density. Do you know much about how much they vary in their density?
The density of the pelloids. I don't. I know that they're porous at times. They're very often porous. A lot of the porosity within the Niobrara is found in the pelloids. But I can't tell you anything about like a number of densities.
Is that the porosity of the whole formation, or the porosity of individual pelloid varies?
What do you mean?
It just occurred to me that if the density varied, then their susceptibility to compaction might also vary. And if that co-varies in a consistent way, you might see different patterns of circularity in different layers.
Yeah, that's something we haven't taken into account. And I don't really know how you would measure the density of such a tiny, tiny little thing.
Maybe immersion.
Yeah.
Thanks.
Something to take into account. Thank you.
In regards to the light versus dark, do you think that these pelloids are different composition, or maybe they get darker as they are more compacted because they're denser?
We think that they're different composition, and we don't really know the exact composition. We're assuming that the lighter pelloids are more calcareous, and that the darker pelloids are more either organic rich, or they have more pyroxene, or they have more like clay.
Manganese? Magnesium?
Yeah. But we're not really sure yet.
That isn't really related to your project, but I'm just really interested in it. I was wondering if this was the first and maybe only basin where the Niobrara is drilled, or is there anything in between where your basin is and where it outcrops in Kansas? Are there more basins, or is there something unique about that depth?
So I mean, the Niobrara has been drilled for a long, long time now. And it's been drilled further east because it's easier. You have less problems with permeability. So yeah, I'm assuming there's basins along the way. Can't name them off, but they're there.
So what's happening, or what do you expect, or what do you think is happening in the matrix? Is there some reason to think that it's similar to one of the earlier questions, that that compaction might be happening even more in the matrix, or even less? Or is it a valid assumption that the pelloids are representative of the compaction behavior of the rock as a whole?
From my understanding, it's a reasonable assumption to make that the matrix is compacting as much as the pelloids, and we're using the pelloids as a measure of compaction for the entire chunk.
All right. Thank you. Oh, one more? Where?
I'm getting scared now.
No. Do you ever think about temperature changing the color of stuff like it does conodonts?
Color?
Yeah.
No, I didn't. I haven't. We always just assume that the composition is what's making the color changes. Because either way, so I'm seeing different pelloid colors within a thin section.
Oh,
So
okay.
you would assume that within the thin section they're going to be in the same temperature.
Okay.